The formation of ions is an important concept. This dictates how ions combine to form ionic compounds, which then participate in double and single replacement reactions. You have been asked to memorize the following pattern. By knowing which charge to anticipate for an ion from a certain family of elements, completing these balanced chemical formulas is as simple as finding the element on the periodic table. Ionic compounds form in ratios that result in a net charge of 0. So if you have a metal like sodium with a +1 charge, it will bond with a halogen like chlorine with a -1 charge, such that the charges cancel each other out. This means that it takes 1 sodium to bond with 1 chlorine. When the charges don't match, such as a bond between magnesium with a charge of +2 and fluorine with a charge of -1, then we have to establish the ratio of how many magnesium does it take to bond to how many fluorines so that it's balanced to a neutral charge. If this molecule contained 2 atoms of fluorine, then the overall net charge would be a +2 balanced against a -2, a net charge of 0. No matter what the charge the ions are, as long as they're balanced to a net charge of 0, they will bond in a 1-to-1 ratio. It's only when those charges are different numbers that we have to use some techniques to establish the ratio that would be a balanced formula. For example, an aluminum ion has a charge of +3. An ion of oxygen has a charge of -2. That is not the same number, and they do not balance. But by doing a method that we like to call crisscross, it establishes the correct ratio. The formula, Al2O3, has an overall positive cation charge of +6 and an overall negative anion charge of -6, an overall net charge of 0. This molecule would contain 2 atoms of aluminum and 3 atoms of oxygen to maintain a balance. Sometimes an ionic compound will contain a polyatomic ion, but again, the ratio of how many are involved in the molecule depends on the charge. In this example, lithium has a charge of +1, and the polyatomic ion of NO3, nitrate, has a charge of -1. Therefore, they will bond in a 1-to-1 ratio because their overall charge is a net of 0. If, on the other hand, you have a polyatomic ion whose charge does not agree with the other ion and the net charge is not 0, then you have to establish the ratio. In this instance, it would require 2 hydrogens to balance with the charge of -2 for the sulfate polyatomic ion. Writing a balanced chemical formula means that the ions within a compound are balanced. The charge of the positive ion is equal to the charge of the negative ion based on how many ions are involved in the compound. This is a different process than balancing an entire equation, which involves coefficients. In this example, it shows diatomic hydrogen reacting with diatomic chlorine to yield a molecule of HCl. The chemical formula HCl is based on the charge of +1 for hydrogen and -1 for chlorine. They bond in a 1-to-1 ratio. In order to balance the equation, we have to use coefficients because we want to show that the number of atoms in the reactants on the left-hand side of the equation is equal to the number of atoms in the products on the right-hand side of the equation. By indicating that the products are actually 2 molecules of HCl, we've accounted for all of the atoms. That is balancing an equation. A double displacement reaction involves 2 ionic compounds that break apart and rebond in new combinations. Let's say we start with the reactants NaCl and Al2O3. In the molecule of sodium chloride, they bond in a 1-to-1 ratio because of their charges. But in the case of aluminum oxide, They bond in a 2 to 3 ratio based on their charges. When these two ionic compounds break apart and recombine, new ratios must be established. When writing these products, we like to use the outside-inside method to make sure that we're combining the correct ions. Always write the positive ion before the negative ion. Therefore, these products would be a molecule containing sodium and oxygen and another molecule containing aluminum and chlorine. But in order to write balanced formulas for these compounds, we have to consider their charges. Sodium has a charge of +1, while oxygen has a charge of -2. Therefore, it's going to take 2 atoms of sodium to bond with 1 atom of oxygen to form that balanced chemical formula. In the second product, aluminum chloride, aluminum has a charge of +3 and chlorine has a charge of -1. Therefore, it will take 3 chlorines to form that molecule. We do not look at the subscripts in the reactants to make this decision. These are new relationships within these molecules, and we look at the charges from scratch. The final step, of course, would be to balance the entire equation. We have to have the same number of atoms of sodium, chlorine, aluminum, and oxygen on the left as we do on the right. In this example, we can see that there are 2 molecules of aluminum in the reactants. Therefore, we want to match that with 2 molecules of aluminum in the product. And there are 3 atoms of oxygen in the reactants, so we want to represent 3 atoms of oxygen in the product. If you'll notice in the products, we now have 6 atoms of sodium in the first compound and 6 atoms of chlorine in the second compound. Therefore, we can go back to the reactants for NaCl and indicate that there would be 6 molecules of that to account for all of the atoms. This is called conservation of matter. In single replacement reactions, there's only one swap. If the single element is positive, it will trade out with the positive cation in the compound. In this case, calcium replaces potassium to form the compound calcium bromide, and potassium then is the single element by itself. Notice that in the formula for calcium bromide, CaBr2 indicates that there is 1 atom of calcium and 2 atoms of bromine. This would be due to the charges. Calcium has a charge of +2, bromine has a charge of -1. It would require 2 of those to balance the calcium. Of course, the final step is to balance the overall equation. If, on the other hand, the single element is a negative ion, it will only be able to replace the negative part of the compound. The new product, potassium iodide, is made up of 1 potassium and 1 iodide because they each have a charge of -1. The other product, bromide, is one of the diatomic 7 and must be a twin pair. The final step, then, is to balance the overall equation. In the end, it's all about the charges. The charges always have to balance. Each time you write a compound, you have to consider the charges.